Hello everyone, today we are doing interviews with professors of the Ruhr-Universität of Bochum. My name is Connor Bergheim and with me is the nice Professor Metzler-Nolte. And would you quickly introduce yourself?
Yes, very happy. Very good idea actually doing this. Thank you for inviting me for the interview.
Thank you for giving us the opportunity.
So, as you said, my name is Nils Metzler-Nolte. I'm a professor of inorganic chemistry here in Bochum since 2006. And I come from Hamburg, and then as an academic you do different stages in your career. And my last position prior to coming here was in Heidelberg, University of Heidelberg, and I was actually in pharmacy, and that has very much to do with what we're doing now. So it wasn't inorganic chemistry, but now it is chair of inorganic chemistry.
Well then, what do you do in your research? Related to pharmacy, I presume, but would you explain yourself?
Yeah. So our research is very much in the interface of inorganic chemistry and medicinal applications, I would say. All the research we do is centered around metal complexes. So that's the inorganic part. We make new metal complexes, but then we go on and explore their properties in biological settings, and typically that means for biological activity, as in either anti-cancer activity, so to kill cancer cells, or in antimicrobial activity, that is to kill bacteria in basically bacterial infections. So that's the broad picture of our research, and we do different metal complexes obviously and different strategies and so on, but much of that is very often it is inspired at least by a biological question or biomedical challenge, and then we do the chemistry behind it.
Okay, that's very interesting. And is there any advantages these metal-based antibiotic or new complexes that have antibiotic activity have over traditional, completely organic antibiotics?
Yes, as an inorganic chemistry, I have to say yes. The question is, what is it? So there are several things. One is you can think of metal complexes that have activity, for example, redox activity, giving electrons or taking electrons, that is, let's say, most easily performed with metal complexes. Of course, there are organic molecules that are redox active. Think of vitamin C or something like this. That would also be a redox active compound. It's more easily maybe realized with metal complexes. Secondly, you can have metal complexes that have specific reactivity. For example, take a metal complex that has a metal chlorine bond, as in cisplatin, and then the hydrolysis of this bond is critical to the mode of action.
Yes, and on that theme, I wanted to ask you as well, do you have a favorite tool, a machine, or an analysis instrument you use in the lab? Or maybe a setup you have that you would like to talk about a bit?
I do. This is it.
Wow.
It looks like a syringe, but it's a tricky syringe. So it is a syringe that has a frit at the bottom. Okay?
This is really interesting. Yeah.
It's very simple, but it has been critical to my career. So why is this interesting? We are making, as we discussed, we are making metal complexes, and we are making a lot of peptide metal conjugates for targeted therapy. This syringe is basically used, we have used hundreds and thousands probably of those in making peptides. So this is a little microreactor. You do the chemistry inside this, so making peptides is repetitive. You pull up the solution, you shake, you put back the solution, you pull up the second reaction, and so on and so on. And the peptide is on the resin, so it's not soluble, it's inside the syringe, and all the reagents come in, go out, come in, go out, come in, go out. In between you shake, you remove the reactions, you pull up, washing solution,
Okay.
So it's this sort of movement, shaking, and then removal again. Well, and that's why the syringe with a frit at the bottom, that's the critical thing. You see the white frit here?
Yeah. Is it glass or Teflon? Or?
This is just plastic.
No, I mean the frit. Is it a glass or is it a
No, I think it's
polymer
also
based?
It's polymer.
Polymer based.
Yeah.
Okay, then the compounds you work on, the peptides, are they suspended in the solution, or are they also like bonded in a matrix?
Yes.
They're bonded in a matrix.
Yeah, yeah. So they're bonded in a matrix. We call it a resin.
Ah, okay.
And so they are immobilized. They don't move, and they are inside this the syringe, and they're held back by the thread at the bottom. So it's not not even a filter. It's not very sophisticated. It's just to hold back the solid material here that is in the thread. But that's why this little device, it costs almost nothing. But this little device is really, really crucial to my research. Without that, I mean, this is a trick that we haven't invented it. It's known in the peptide community. But we had the first colleague who taught us how to make peptides. He brought a couple of these syringes with him and said, you need to buy those if you want to be a peptide chemist. And that's what we did.
I mean, it's the most simple tools that makes the most difference. And if you use a tool like this 100 times a day, then it better be simple and practical. Well, we're gonna go back a bit now with the questions, and I want to ask you, how did you get interested in chemistry, the field of chemistry, in the first place? Like, where did you start?
High school.
Yeah?
Yeah. High school, I had a very good chemistry teacher. Originally, when I was a young man, if you like, I wanted to become an engineer. I liked playing around with radios, and soldering and building my own radios, and I was going to become an electrical engineer until I realized when you do that, you're actually not building your own radios, but you're dealing with mathematics most of the time, and it's all theoretical, and I didn't like that. So, and then I had a very good chemistry teacher, and I realized when you become a chemist, you actually work in the lab, like this. You work in the lab quite a lot, and that's what I wanted to do. It's something that is intellectually challenging, it's interesting, and it's a combination of, sort of theoretical or conceptual work, brain work, and manual work in the lab.
Yeah, it's a real skill you have to learn, and I guess the better you get at it practically, the better of a researcher you become, and it's really nice. Like, there's not many fields of research that have such an interconnected way of dealing with the things you're working on.
I like doing things manually and building things. I also like working in the garden. To tell you the truth, I'm actually not a very good chemist in the lab. So I'm quite happy to let my students do it. No, I mean, it's kind of okay, but I had colleagues when I was working in the lab full time. I had colleagues who were much more skilled and much better in, actually doing tricky reactions, let's say. So in that sense, although I like working in the lab, my students, they get scared when I come into the lab and I'm asking for something, and I say, "Oh, let me do it. Don't touch anything. Let me do it." So, but the motivation was definitely, making molecules and making things was absolutely a motivation, and the more you get into it when you actually study chemistry. I mean, you all know this. There is an excitation. I mean, you have to be excited about working in the lab.
Absolutely.
If you are, if you don't like the lab work, then chemistry is not for you, I would say.
Yeah, it becomes too abstract, I would guess. Yeah. This is the nice thing, it makes it not abstract. Yeah. It actually seems like a useful skill. Your brain just loves to remember it all when you do it practically. Yeah. And also, why did you then decide to even step it up and become a professor after your PhD and after your postdoc?
Yeah. I mean, I cannot really say the aim was to become a professor, because, as you know, the career in academia is difficult, and it's most importantly, it's unpredictable. So it's very difficult to really say, this is what I want to be and where I want to be. What I could say is that when I was towards the end of my PhD, or maybe postdoc time, I really wanted to work in industry. I wanted to work in a large research lab. BASF, for example, Ammon Labor was at the time one of the big research labs, and I really wanted to work there because I wanted to work on sort of problems of societal relevance, so like sort of large-scale problems, and I wanted to have a lot of international exposure. Yeah? I like traveling, I like being with different people, and I thought a big company offers you, possibility to go abroad, to maybe work in Singapore or work in Hong Kong or whatever, where you want for some time, and you have that only in a big company, obviously.
Yes.
And then after some time, I realized, well, the things I really liked or thought I like, you actually have in academia as well. So you have a lot of international exposure. You can actually choose your own problem where you want to work on. So you can pick something that you find interesting, and you basically work in an environment where you have a lot of young people and a lot of challenges all the time, which I like. Well, so this led to a postdoc, and then led to the first contact to my former. I was working in Mülheim at the time as a independent group leader, if you like, and this led to the first contacts. And I was always conscious that there is no guarantee that you become a professor. I said, okay, I can follow this path, but I always had a second option as well. I always thought about a plan B in case you don't get an offer as a professor, which is very likely to happen. I mean, I had several colleagues who were clearly at least as smart as I am, but they didn't get an offer for various reasons. And so I always had a plan B. And then, of course, I was lucky, as I said, I got this position in Heidelberg, which was my first position when I was, 32 or 33, so relatively young. And that was lucky also for the family, of course, at the time. And then later on I got the position in Bochum. And so it worked out very well, but there was absolutely no guarantee. So it was always a plan B, something to do something outside academia.
Academia is a pretty tough road to go down.
Yeah.
Here in the lab of Professor Metzler-Nolte, and today he's showing us the peptide synthesizing.
Yeah. So unfortunately, this is not working at the moment. There would be bottles attached here for the different amino acids. You see, for example, glycine here and alanine. So it's not working at the moment, but this is where all the amino acids are. And this is inside is a microwave reactor where the peptide is actually done. We talked about, the syringe. So what the student way of making peptides, like shaking this and removing and so on. The shaking is actually done inside here together with the microwave heating. So it's fast and efficient. And then the sucking up the solutions and removing it is actually done via these tubes here, and then there's a waste container in the back, and the reagents come in this way here. So what you do manually, when you go into a bottle and pull up the solution and remove it, this is all done here. It's computer controlled. Here is the computer on the other side, so it's computer controlled. And you can program the sequence of amino acid, the length of the reaction, and so on and so on.
Is there a syringe body at all, like in this down here, or is there a different kind of container?
Yeah, it's a different kind of container, but basically it has the reactor as well, and of course it has the filter frit, so to speak. There is a frit at the bottom as well. Exactly, in order to keep and then in order to keep the solution inside and the resin inside, and then there is air applied here, so there's a pressure of air in order to push the solution through. So this is all done here. There are the valves here, and this is connected to the bottle of nitrogen which you see there. And this is what builds up the pressure and then pushes the solutions around.
So we are standing here next to a very interesting machine that is used in the analysis part of Mr. Metzler-Nolte's work. Would you like to explain it?
Yeah, sure. This is a gel documentation system. So when you have, for example, a gel with DNA, you separate the DNA strands, for example, and then, of course, you want to detect, for example, let's say we do this in a lab practical for students also. You have a DNA strand, you treat it with a metal complex, and you shine light on it, and then the strands are cleaved. So this is the reactivity. We talked about reactivity for metal complexes, Ross production, for example. You can use it to cleave DNA. And you got smaller pieces of DNA then, and of course you want to see this. So you take a gel to separate the bands, the different length of DNA, and then it's put inside here. The gel is put inside here, and in this in the DNA you insert a fluorescent dye. you put the gel here at the bottom. There are two UV lamps up here, so they shine light on it, and then the individual bands, they shine up, so they light up, so they shine. And there's a camera here on top. You see the camera with the lens here, and you focus, and then you can basically take pictures here of the gel with the individual bands fluorescent. So in this way you can analyze how many strands do we have. Is it cleaved maybe just once, or is it cut into many pieces, and so on. And we synthesize metal complexes who do this in a controlled way. Yeah? Okay. And then you can investigate, depending on the sequence of the DNA or on the metal complex, for example, did it do it well or not so well, high concentrations, low concentrations. This is what we use to analyze.
Can you use the gel plates also for peptides? Isn't there also a gel electrophoresis of peptides?
For proteins, yes.
Peptides
are too small, typically. We use chromatography, which we saw upstairs, HPLC. We use chromatography for peptides, but for proteins, you use gel chromatography. And that would be the same principle. In principle, also the same machine. It would depend if you want fluorescence detection. It's very easy because in DNA you have these intercalating dyes, which you add afterwards. For proteins, you would have to put on some fluorescent tag from the beginning. So this is not as frequently done. But in principle, it's the same principle, it's the same machine. We have also used it for protein gels, but for different applications.
One last question before we end the interview is when PhD students, master students from this university, maybe other universities, are interested in your research group, your research, what do you expect them to bring with them in terms of knowledge or skills, or everything around it?
I guess everything around it is the most important. That's curiosity, of course. Open-mindedness and curiosity. In terms of skills, we do expect skills in interest and skill, of course, in synthetic chemistry. So synthesis. That includes, working in Schlenk lines and in vacuum sort of vacuum devices. Let's say Schlenk lines, for example, glove boxes. And also some interest in biochemistry, for example, is in peptides or is in thinking about cells and so on. It's interesting and challenging in the sense that it's actually quite a broad field. When you think of it, from small molecules to thinking in cellular context is quite a broad field. So that is why I'm saying there is a certain degree of curiosity. I guess that's the two things. I mean, you have to be interested and skilled to work in the lab, because in reality what we do, although when we talk about it, when I give a talk, it sounds as if we're doing a lot of biology and we're working on these big medical problems. The reality is 70 or 80 or whatever percent is working in the lab and making new compounds. And I guess you all know this, you fail more often than you succeed. Right, so failure in the lab is built in. It's the same in our group. I mean, during my PhD, I think 70% or so of the compounds I try to make failed, and you live from the 20 or 30% that work, and maybe it's a little bit better in some project here, but definitely you have to be interested in lab work. You have to be excited by lab work and making things, and accepting failure as well, and then move on with the things that work, the 20% that work. You move on to biological experiments, and then you hopefully find something interesting. Well, so that would be my expectation, sort of to be interested in lab work, to understand that frustration is part of the job, and to be excited about the 20% results that you're getting.
Yes, well, with enough passion for chemistry and biology, there certainly is a way to come over the frustration of unforgiving lab work and unforgiving results. So, thank you very much for the interview. It was very nice, and we are very thankful. We could ask you so many questions and pick your brain a bit.
No problem.
Well, thank you very much.